Well, hello there. I'm Venkatesh, and today's topic is topology in structural engineering. So, let's have a simple introduction to it. Structural optimization is concerned with maximizing the utility of fixed equality of resources to fulfill a given objective. Uh, so, basically, the optimization structural optimization exists in shape, size, and topology. um, Structural topology optimized most general in three categories. They are the number, location, size, and shape of opening with the continuum, etc. The modern topology optimization technique can be applied to generalized problem through the use of finite element method as a relatively recent innovation, and aerospace, automotive, and mechanical engineer have successfully utilized topology optimization in order to achieve weight saving in the structure. However, in this era of situation where the concept redundancy play an significant role, we should reconsider the optimizing every single structure to the best of its efficiency. Indeed, uh, the one of nature of every civil structural engineer project necessities, it uses a rigorous optimization technique to drive efficiency on increasingly complex projects of today. So we can see structural engineering in every aspect of world. Many monuments follow this. This is the one of the first processed solution of to the structure of topological optimization problem, and it looks like this. And topological optimization has found several applications in the field of civil engineering, mostly notably a novel technique for geotechnic analysis and reinforcement layout optimization in concerned structure. The main focus of this review study is application of topological optimization to the design of large scale structures and large scale structural engineering components. In present, the theoretical background of the practical implementation of the most commonly used solid isotropic material and pentana. I will write it down. That is SIMP, solid isotropic material with penalization, SIP. This is a technique, and reveals the previous technique of topological optimization in both structural engineering and architecture. Moreover, the implementation of topology optimization within the field of structural engineering and potential opportunity behind the present are examined through various examples. So the first one will be So here are the some of the applications for topological optimization. So let's see its background of topological optimization. During in 20th century, architects and engineers have used to innovate and novel the method of development of optimum form of structures and sculptures which we see today. Of particular note would be the work of just a minute. So these are the some of the scientists who actually worked on this topic in 20th century. All these individuals shared the key theme, attempting to create a structurally efficient and functional forms that are architecturally pleasing at the same time. Topological optimization, which has been used randomly in the structural design process and has no clear defined role. It has been described as an intellectual sparring partner during the earlier conceptual design phase. In some case, the result of topological optimization study has been directly translated into geometry of the final structure in the process called as computational morphogenesis. The result of many topological optimization excess often show a strong resemblance to structure that are formed in nature and are usually naturally efficient as well as pleasing. As I mentioned about the application of topological optimization in structural engineering, the optimization has been presented like engineering skilled more oveling and that is called as SOM has utilized the theoretical work of high rise bracing design. Oh, sorry. High rise bracing design in order to develop a conceptual design of high rise buildings that are both ethically pleasing and structurally efficient. There is a famous famous station that is Takisuki. I'll write it down better. This is the best example for the optimized structural engineering, where it takes minimum space to optimize the structure. It has found that the resulting form has a strong resemblance of a tree trunk. Indeed, it looks like a tree trunk. Uh, and Another support structure of Dobie carved roof canoe has designed using topological optimization, and the constructions for reinforcement concentrate uh, has shown in some of the famous structures. Computer numerical controlled, that is CNC mining technology has uh, employed the create of framework for some of the geometrical complex topological form. In general, manufacturing practice are required in case where topological optimization design are implemented in a very large scale. Uh, so how actually topological optimization technique works? We in terms of topology is derived from Greek word topos means position. The application of topological optimization extends to the number of holes they're located, their shape and connectivity of the structure, shape and size optimization are more limited than topological optimization. In the respect that the designer must specify the topology of the pros, uh, proposed structure, which is then fixed through the optimization structure. The general form of topological optimization problem is to derive the optimum disturbance of material within a designable domain to fulfill a given objective. You are seeing a diagram of which basic terms used in topological optimization. These are some of the basic terms which are used in topological optimization. There are once again currently two popular ones that are two popular techniques that are solid isotropic material with penalization, that is SIMP technique, and evolutionary structure optimization, that is ESO technique. Both of them involve in designing domain with finite elements and utilize the FE analysis technique that to determine response of the structure to optimized. ESO has received significant research interest in generally criticized for being no horrible technique that does not guarantee converges to an optimum solution. The SIMP technique is generally accepted in the lecturer in the literature as being the most has been most prevalent tool for the topological optimization of the linear elastic structure. The solution method of non-linear dynamic and bulking response are currently under investigation. They are not yet a stage for maturity, and the only equivalent static load method, that is ESLM. The lack of technique in solving the problem involves the more complex behavior is the major barrier to more widespread implementation of topological optimization in the civil engineering and also structural engineering. As in the video we have mentioned about SIMP technique very much. So let's see what it is. The basic of SIMP technique is to determine the optimum structural shape of varying the density of material within the designable domain. The designable domain is generally discretized, while the FE analysis technique is employed to determine the behavior of structure to be analyzed. The use of a discretized design shape may be considered thus. One may consider a design domain as a black and white TV or television screen divided into a lot of small pixels, that is a finite number. By turning the material on and off in the each pixel, one each can produce picture of optimal structure. You could have experienced if you have seen the SIMP technique involves FE analysis of designing space followed by optimization of density of each finite element within the mesh. The structure with the altered element density is the re-analysis of optimization performs again. The procedure continues until it converges. The intermediate density material, which neither takes the value of solid or void, in general not desirable, since it is not possible to correspond each intermediate density in the real world structure. In order to avoid the presence of intermediate density within the final design, a penalized is used to disproperty decreases the benefit, derive the presence of intermediate density in material penalized. Now intermediate density is arrived within SIMP. It is related to stuff which is write it as E is equal to this is the symbol of density rho. There are two basic approach to topological optimization SIMP technique. In SIMP technique, minimum compliant design, minimum weight design. The minimized of mass of a structure within contrast on the specific performance measure. The specific performance measure is usually be defined as stress, displacement, bulking load factor, or any combination thereof. And we have seen the application as earlier. Now we take up a rise high structure design, how it exactly be. Requirement of high rise structure is a solution to overcrowding the modern cities and as landmark process significant challenges of structural engineering. These challenges elegant describe the premium of height effect, whereby the material required to construct a taller buildings is disproportionately greater than for low rise construction due to the increase of bracing requirements. As even more significant structural challenges in 21st century is the increasing tendency of architectural aspirants in high-rise construction to tend towards aerodynamic, twisted and free forms. Geometric complexity of twisted and free form structure often causes engineering to fall when attempting to determine the optimum structure layout. An overall of an investigation into the use of topological optimization for the design of geometrical complex high-rise structure conducted by the author is presented. The optimizing complex high-rise structure in order to civil engineer community to use the topological optimization technique is high defined geometric complex in high-rise proposal is of tower with a free form architectural intent has sought. In the bionic tower is an architectural proposal. This is a rough diagram of that tower, which is in Abu Dhabi. The project reached the feasibility stage in 2007, but has never processed as an investigation has conducted here to determine the topological optimization could have been used to conceptual structure design phase. The brace outrage structural arrangement has selected for bionic tower whereby the structure core is stabilized by the serial of structural element of perimeter of the building. The core connected by the external bracing element of truss. The tower, the braced outrage has selected one of the basic that fulfills architectural intent. The core is connected with the perimeter column. We can see in the diagram perimeter column by a series of horizontal traces. Literally loading has applied the tower and topological optimization studies were preformed on an entire exterior surface as well as perimeter of a surface. Despite of highly irregular shape of the tower, it has found that a series of discrete structure load path could be identified in form resulting the topological optimization. Um, an inspection of the traces connecting the core of perimeter surface showed completely rational, and furthermore the aesthetic of its structural layout were compatible with the freeform architectural initial intent of architect and the client as well. Precisely, it is worth nothing that the topological optimization technique has been applied to a structural design of irregular and twisted high-rise structure. Previously, however, the example presented in the first of its kind where the topological optimization has been applied to a completely free-form geometry, the result is actually a fail. You know. the topology the topological optimization in structural design of a member. This is a diagram of castellation technique, and the judicial placement of hole in a web of a steel beam has been employed to design a lighter and stiffer beam for over 100 years. Original concept of creating a beam with a web opening can be attributed to uh, the scientist. Just a minute. Here's the scientist who patented now known as castellated beam. The castellated beam has formed the expansion of parent one section to form a deeper stiffer section with web opening. The circular beam, which contains circular opening, are currently the most widely used perform perforated beam due to their beneficial weight to stiffness ratio and the ability to pass service. Example, hydraulic pipes, electric wires, etc. Their large holes, while the stress is distributed evenly in circular holes. The alternative castellation process